Welcome to the solutions to the waves and sound problem set, problems number 15 and 16. Problem 15, one of the strings on a violin has a fundamental frequency of 196 hertz. It is 30 centimeters long and has a mass of 0.5 grams. While this string is sounding, a nearby violinist effectively shortens the same string on her identical violin by sliding her finger down the string until a beat frequency of 2 hertz is heard between the two strings. When this happens, what is the effective length of her string? We're going to start off by labeling some, drawing some diagrams and labeling some things we know based on what we're given in this problem. We know for violinist 1 that her string is 30 centimeters long, 0.3 meters long. We know it's vibrating at the fundamental frequency, and we know what the standing wave at the fundamental frequency looks like, and that's one antinode. We know the fundamental frequency is 196 hertz. For violinist 2, we're told that she slides her finger down the string until a beat frequency of 2 hertz is heard. Therefore, when her string is vibrating at its fundamental frequency, by shortening the string, that's going to make the frequency go up. So with a 2 hertz beat frequency, that tells us that her fundamental frequency has to be 198 hertz. Goes up by 2 hertz. Our job is to figure out the length L of her string, and then we'll be able to figure out how much she shortened it by, even though they're not asking us. It's interesting to look at. All right, so we're going to start by taking a look at string 1. And start with the wave equation, V equals F1 lambda. What we're doing is we're figuring out the speed at which sound travels in that string. We know the fundamental frequency is 196, and we know the wavelength is twice the length of the string itself, since there's half a standing wave on that string. So if there's half a wavelength in 0.3 meters, a whole wavelength would be 0.6 meters. Multiplying the two, we get a speed in that string of 117.6 meters per second. We are reminded, back up in the problem, that the second violinist is vibrating the same string and has an identical violin. What does that tell us? It tells us that the speed of the sound in the second violinist string is exactly the same as the first one. So now we set up the wave equation for string 2. We know the speed for string 2 is identical to the speed for string 1, 117.6, and that it's vibrating at its fundamental frequency of 198 hertz. Again, it's vibrating at the fundamental frequency, so the wavelength is equal to twice the length of the string being vibrated. So 2L. We solve for L and we get 0.297 meters. And this, of course, would be 29.7 centimeters. Really neat to consider in this problem that she only had to move her finger 3 millimeters to make that difference. Gives you a lot of appreciation, especially for professional orchestras and how well they sound. Okay, let's move on to problem 16. A flower pot is knocked off a balcony 20 meters above the sidewalk and falls towards an unsuspecting 1.75 meter tall man who is standing below. How close to the sidewalk can the flower pot fall before it is too late for a warning shouted from the balcony to reach the man on time. Assume that the man below requires 0.30 seconds to react to the warning. Okay, this actually is a neat little kinematics problem, and really all the difference here is that it's using the speed of sound as part of the calculation. So after a good diagram, we're going to start by calculating how long does it take the sound to get to the man's ears. So we're going to do a V equals X over T. We're not told the temperature of the air, so we have to assume standard temperature and pressure. So we'll use 331 for the speed of sound. And the distance that sound travels is the 20 meters minus the 1.75 meter height, assuming his ears are near the top of his head. So another assumption, though not totally true, we'll have to assume that close enough. It takes then the sound to travel 0.055 seconds to reach the man. Now what we're going to do is we're going to take and calculate the total time for the shout to reach the man and for him to react. So what we're going to do is add the 0.3 seconds it takes for him to react to the total time for the shout to reach him. And then we're going to use that time later on to compare how long it takes, the distance it takes, the distance the pot can fall before it's too late for the guy to react. All right. Next we're going to calculate the time it takes for the pot to fall just by itself. This is a pretty simple kinematics problem. xy equals VOYT plus 1/2 GT squared. The pot falls 18.25 meters if it's going to impact his head. Starts with no initial velocity because it's dropped, plus 1/2 9.8 t squared. Important to ask whether or not we have conflicting directions in this problem. The xy value is 18.25 meters down, the 9.8 is down. So no, we don't have conflicting directions, so we don't have to worry about the signs. We solve for time and we get 1.93 seconds. All right, the next part is the critical part of the problem. What we need to do is we need to take the 1.93 seconds for the pot to get to the guy and subtract the time it takes for the shout and his reaction time to happen in order to figure out how far can the pot fall before it's too late for the shout and his reaction to get him out of the way safely. So we subtract those two and we get 1.575 seconds. We're now going to use that time to figure out how far the pot can fall during that amount of time. So xy equals 1/2 9.8 1.575 squared. When we calculate that, we get 12.2 meters. So this is the distance, how far the pot has fallen. However, they ask us how close to the sidewalk can a flower pot fall. So they want the answer relative to the sidewalk, not relative to where it was dropped. So all we have to do is subtract the 12.2 from the 20 meters, and we get a height above the sidewalk of 7.8 meters to 2 digits. We could probably do that answer to 3 digits. I don't know what that is. 7.80, I have no idea. It doesn't matter. All right, so there's your solutions to 15 and 16. We will be doing problems 13 and 14 in class tomorrow.